¿Funciona?
So can you give me a sign when it's like 5:45?
Okay.
Yeah.
Okay. Hay dos sitios por ahí también. Vale.
I'm fine, thank you. Nice to see you.
Bueno, pues muchas gracias por venir. Ya sabéis la semana que nos espera, que va a ser bastante interesante. Hay mucha gente por aquí, al final no nos ha hecho falta movernos, así que bueno, si tenéis alguna pregunta, al final podréis... Bartosz, I don't know if you mind that they raise their hand for questions during your talk, or better after the talk?
Oh, during the talk is
Okay.
fine, yeah.
So, well, the talk will be in English, so I will continue in English. And Bartosz is going to stay in Madrid for a week from Monday to Friday, and we will also give some seminars about a couple of papers that we have prepared, and I hope that you enjoy it very much. So please, an applause for Bartosz. And
Well, thank you very much for inviting me here to this beautiful city. I like this opportunity because every time I have to prepare talks, I don't like repeating myself. So I take this as an opportunity to maybe learn something new and talk about it, because like this is the best way to learn stuff when you have to explain to other people. So this time I will talk about category theory, because obviously that's kind of my thing, talking about category theory. But I also looked into type theory, and there is this whole interesting spectrum between hardcore engineering, computer science, and mathematics, and very abstract mathematics. It's pretty amazing how these things recently converged. We have, on the one side of the spectrum, we have things like Turing machines, which sort of like are assembly language programming. But then we have lambda calculus, which is more of a mathematical approach to computation. And then we have mathematical logic, which is a very, very ancient part of mathematics. And then we have like the latest developments in the foundations of mathematics, which is homotopy type theory. And it's really amazing how all these things come together, like and they feed on each other. So development of computers and programming actually led to some developments in foundations of mathematics, and vice versa. People are taking ideas from the foundations of mathematics and implement them in computers. So this is a very, very interesting times where we see this amazing convergence. So since we are talking about programming, right? Programming, especially functional programming, is, as we understand it, is about types and functions, more or less, right? So when we write something like f is a function from A to B, right? this is what mathematicians would write, right? In Haskell, we would put a double colon here. That's the only difference, right? What does this mean? So this thing can be understood on different levels, and you can go as deep as you want into it. So A and B are types, right? So f is a function from type A to type B. What's this arrow? We can look at this arrow and saying, okay, it takes two types, A and B, and produces a new type. It's a type of function from A to B, right? So f, so this is really saying that f is of the type A to B of a function, right? So in order to understand this, we really have to ask, first of all, we have to ask the question, what is type? What is type and what is function? And it used to be that I would just simply say, oh, okay, everybody knows a type is just a set of values, right? And this is a set theoretic approach to programming that used to be okay, right? But really, a function, when it's implemented in a computer language and then even executed on a computer, right? It's not really the same as a mathematical function. I mean, a function takes time to compute. It goes through certain steps, right? I mean, usually as programmers think of functions, it's mostly thinking about an algorithm. So things that take time to execute. And in particular, we are very interested in, is this fast enough, right? Because we have to write faster and faster programs. And so this part is totally not taken into account in the mathematical approach. In mathematics, a function between sets, well, it's just a set of pairs. One element from one set, one element from the other set, right? It has to satisfy certain properties, but it's essentially a set of pairs, which means that the values of a function for a given argument are already given. You don't calculate it, it's there, right? So this aspect of going through the calculation and how long will it take, how many steps it will take. Even if you don't execute it on a computer, you can always ask the question, well, how many steps does it take to reduce this expression to the simplest possible and get the result, right? So you can count the number of steps. And this is just the beginning of the problem, because now if you want to have a powerful, expressive computer language, then you introduce things like loops or recursion in functional programming, right? And once you get into this, into general recursion, then you can write functions that never terminate, okay? And not only that they don't terminate, I mean, it's easy to write a function that doesn't terminate, and you will see immediately, oh, it doesn't terminate because it calls itself in an infinite loop, right? But we know that it's even theoretically impossible to predict whether a function will terminate or not, right? This is the termination problem. Like this is something intrinsic in the theory of computation that we cannot even tell. This is a problem that cannot be answered. There is no algorithm to say whether this function will terminate or not. So in Haskell, for instance, people deal with this, sort of hand-wavy thing most of the time, saying, well, first of all, let's assume that all functions that we write terminate, right? So then we can use the simplified model in which we treat types as sets and functions as functions between sets. Or we can say, well, we'll just enhance this model by saying types are sets, plus every type has this additional element called the bottom, right? This is just in case the function never terminates, then it returns a bottom, okay? Because if you have a function from integer to integer, it can give you an integer at the end, or it might never terminate, in which case it produces sort of conceptually a bottom, which must be, therefore, an element of integer. And of course, then, okay, so some people say you can't even define integers in Haskell because of the bottom problem, right? It's like, is bottom an integer? No, it's not, right? It's not in the normal definition of what an integer is. So this is where this idea of sets and functions really starts breaking down, and there's even more to it. We have polymorphic functions in Haskell. I mean, in every sensible programming language, we will have polymorphic functions, right? And polymorphic functions are described by this so-called system F, which is a very nice system that's sort of axiomatically defined and defines how things are executed and so on. And people were trying to say, okay, so if we have system F, can we model it in set theory? So assuming that types are sets, how does system F work on sets? Okay? And Reynolds wrote this very good paper about system F, in which he showed these things that are now called theorems for free parametricity, right? And he based it all on set theory. And then, I don't know, a year later or so, or a few months later, he wrote another paper saying, no, sorry, I made a mistake. This does not work. System F cannot be described in set theory. So we know that polymorphic computations really are a little bit outside of set theory. It's not totally outside of the set theory, because then some other people wrote other papers and they proved that if you just take the constructive part of the set theory, then you can fiddle with it. So this is when people started talking about categorical semantics. Let's just forget about sets and start from scratch, because sets, even the set theory, even in mathematics, is considered a little bit like assembly language of mathematics. It just assumes too much. It's not general enough. It just assumes things about sets. In particular, a set has elements. Now, is that really necessary to talk about elements? And you might think, okay, well, like we have variables in programming, right? Aren't they just elements of types? Yes and no. So this is a question that can be bypassed, and it turns out that it's better to describe the semantics of programming using more abstract language than sets. And then there is, speaking of types, there is type theory. Okay? Type theory was developed in the 20th century, and in particular, there was this guy, Martin Love, who defined type theory as we know it now. And And this definition of type theory, I mean, he was actually working on type theory more from the logical point of view than from the programming point of view, as far as I know. And it's a theory that doesn't assume too much. So it's an axiomatic theory. It just says, we don't know what a type is, right? Type is this atomic thing, you know. We don't describe, we don't go inside the type to say what it is. We just assume that it has a certain set of properties, okay? So why don't we define types by just assuming a minimum set of properties? What is the absolute minimum of set of properties that we can use to describe a type system? Okay? And then it turned out that the same theory, the theory of types, can be used to describe mathematical logic. And that's the Curry-Howard isomorphism. So these guys, Curry and Howard, came up with this. They looked side by side, you know, at here's logic. These are the rules of logic. Logic is also defined axiomatically. So there are these things called propositions, okay? Now, on the one hand side, you have propositions, and how do you form new propositions from other propositions, right? A proposition is something that you can say is either true or, it's a statement, like, is it true or false? You know, it's like, is it true that my name is Bartosz? Okay, it's true. So it's a proposition that's true, right? And you can form combinations of these propositions. And especially the interesting ones are like, suppose that something is true, then can you show that something else is true, right? So that's like the most interesting part of logic. And when you look side by side at Martin Löw type theory and logic, you see not only that they are similar, they're actually the same thing. Okay, it's like because these are axiomatic theories, then you don't really know what a type is or what a proposition is. You just look at what their properties are. How do you form new propositions from existing propositions? How do you form new types from existing types, right? I mean, we know a little bit about how to construct types from programming, right? We produce new types using products and sums and so on, right? It turns out that in logic, we use the same things, right? But there is one little difference, that the logic that's described by type theory is a little bit stricter than what logicians used to do. The thing is that it's logic in which proofs are relevant. That if you really want to have a good theory of logic, then you also have to talk about proofs. Like if A is true, then B is true. What does it mean? It means that if you can prove A, then this is a proof of B. Okay, so that operating on a proof of A, you can get a proof of B. Okay, that's like a revolutionary thing, and mathematicians have been dealing with this for some time. There was this guy Brouwer who came up with these ideas of constructive logic. So constructive logic or proof-relevant logic is logic in which you cannot say that something is true unless you can prove it. Okay, that seems like makes sense, right? Normally, but this is not what mathematicians do normally. They assume that things are true when they can show, for instance, that the opposite is not true. Okay, And this is also something that we are so used to thinking, you know, this is like, well, it's either true or false, right? It cannot be neither, right? But if you don't have a proof of something, then how do you know that there is not a third possibility? And this, interestingly, this ties very well with this idea of functions that the halting problem, right? Because you have functions that evaluate to something, and then you have functions that go forever, right? And you cannot say which functions will terminate and which can, I mean, in our arbitrary case, there is no procedure to say whether the function will terminate or not. And this is very much in the spirit of, well, if you have a proof of something but it runs forever, then it's not a proof, right? So constructive mathematics is so much closer to programming, because if you write a program that runs forever and never evaluates, then it's useless, right? So this whole area of constructive mathematics and constructive proofs and type theory became like a really new trend in mathematics. A lot of mathematicians don't like it and say, this is like, what, you can't have the law of excluded middle, are you crazy, right? But there are more and more people who are convinced that this is actually the way, and especially people coming from computer science are saying, well, obviously, if you cannot evaluate something, then there's no way, right? So the simplest thing that like the beginning of type theory, and this is why it looks so much like programming. It's like you have this judgment x. We read this that x is of type A, without saying what x is, what A is. But this is how we pronounce this, and this is so much in the spirit of programming, right? This is a variable x, and this is a type A. So just to understand this is an interesting thing. So like type theory itself will not tell you what it means. It will just say you, well, if you can say this, it could be true or it could be false, right? No, actually what it means is you can take this statement in type theory that x is of type A, and you can translate it into a logical statement directly. And what does it mean in logic? It means that x is a proof of A. Okay? So every time you have a type, if it has elements, okay, then this type corresponds to a true statement in logic. And in particular, well, the interesting statements are of this type. Is there a function from A to B? If you can implement this function, f, then you have proven that it exists. Okay? So this is like the beautiful merging of computer science and logic. So let me give you maybe like a taste of this, right? It's like suppose that you want to construct a what is called conjunction of two propositions, right? So A is true and B is true, then A and B is true, right? So in logic you would write it something like this. I mean, in type theory, this is how you would write it. You would say A comma B is of type A and B. Okay. So let me explain what it means. Okay. These are the assumptions, and this is this is what you have to assume, and this is what you can construct. So this is a construction. All this stuff is about constructing things. So you say A is a proof of capital A. So this is a proposition, right? And this is its proof. So I have a proof of A, and I have a proof of B. Now I can take these two and form a proof of A and B. This is a new proposition, A and B, right? How do I form a proof of these two? I make a pair. Given these two proofs, it proves that A and B both have to be, right, true. But I have an explicit proof of A, an explicit proof of A, and this is the construction that constructs a new proof of A and B. Now, this looks very much like what we call in programming a product, right? In order to construct a product, you need an element of type A, and you need an element of type B, right? And then you can construct an element of A cross B, okay? That's the product type, a pair type. We call it pair type, right? It's identical. And so this is how you can construct new propositions and how you can construct new data types. A product type is a new data type, right? A pair type. But how do you do computation? Well, you do the computation by saying, okay, let P be, so in logic, you would say, P is a proof that A and B is true, okay? Then there is this thing called first of P that is of type A, okay? Now this looks very much like programming, right? But this is in type theory. This is in Martin-Löf type theory. It's called the elimination rule, okay? And in programming, this is saying, you know, if P is of the type A cross B, so it's a pair of an A and B, then there is a function called first that if you give it a P, it will give you something of type A, right? The first element of the pair. So we know how to construct a pair, right, from two elements, and then we can eliminate a pair using this rule. And this is how we compute stuff. Okay? Of course, there is more to computation, but this is like the general framework in which these things are computed. Okay, so where does category theory come into this? So category theory provides a much more general framework for this. Okay, so in particular, you can model these things in category theory. And since I've tried to convince you that logic and type theory are the same thing, really, at least constructive logic, then it means that in category theory, you can model constructive logic and you can model type theory. Okay? And category theory makes fewer assumptions than set theory, therefore it's more general. So you can have, you can have a model of type theory in set theory as well, but it will be a simple model. It won't encompass everything. But category theory is much less demanding. It has fewer assumptions. So it's sort of like asking the question, what things can I throw out and still make sense, right? And one of the things that you throw out immediately when you start from set theory is this idea that sets have elements. So how much can you say about sets if you throw out this information that sets have elements? And it's an interesting question, and we'll go through like lots of constructions. So my plan is to actually go through lots of constructions in category theory, and then give you immediately the idea what they mean in programming and what they mean in logic also. So it's sort of like a side effect of doing category theory and doing programming. You'll get like a little introduction to logic. Very simple stuff, you know, things like conjunctions, disjunctions, and so on, right? But it's very interesting to see that. And then at some point, when you go into like advanced Haskell programming and so on, then you will often have this double vision when you see here I'm implementing a function, but you look at the types and you can think, okay, if I have a proof of this, then I have a proof of this. Looking at it in terms of proof theory, and it gives you a totally new perspective on programming. And what is nice about category theory also that it provides a very a good graphical language to describe these things. So the thing that I wrote here as a product, for instance, you know, in category theory, you have a product as well, but you draw a picture like this. And you call this first, and you call this second. Okay? So this whole, the information that I gave you in this, well, I gave you first, right? So I gave you information about this. That if you have A cross B, then you can get A out of it. That's called a projection, right? So category theory provides you with this nice model of both type theory and logic, and it also gives you these nice diagrams, pictures, that are kind of easier to understand. I mean, some of the constructions in type theory get really involved, but once you draw a picture, it's like, oh, okay, that's obvious. And this idea that you throw away elements of sets, you throw away the idea that sets have elements, and then you just work with what we call in category theory objects. So instead of sets, you have objects, right? And this idea corresponds to, in programming, it corresponds to the fact that we want to define things more in terms of their interface rather than in terms of their implementation. We don't want to go into details of implementation in order to understand the data structure, right? We have these object-oriented programming. It's all based on this idea of data hiding. That interface is more important. Well, in functional languages, the interface is mostly about, you know, function types and so on. But this idea that you throw away information about what's inside the object and instead describe objects in terms of how they interact with other objects is essential in category theory. So this is the plan for these talks, that I'll be talking about category theory, and for every construction in category theory, I will tell you what this construction means in logic and what this construction means in type theory, which is the same essentially. It's just a different notation, right? And we'll see how far we can get with this. So, maybe without any further ado, let me just define the category for you. Okay, because this is like the beginning of everything. And you'll see how simple the definition of a category is and how natural it is. And also how amazing it is that using this such a simple language, we can express so much that you'll see in the following lectures, what we can express. So you start with a category consists of objects and arrows between these objects. So that's simple to understand, right? So you have objects, and you don't ask what an object is. So this is like more of an axiomatic approach that you don't say what an object is. You just say, I have an object and I can call it a lowercase or capital or whatever you like, right? This is another object B, right? And I can have an arrow between these two. And these arrows are called morphisms. So sometimes I will say morphism, sometimes I will say arrow. It's the same thing, right? So if I were to be more formal, I would say you have a collection of objects and a collection of arrows, okay? And it's important to say collection rather than set, because we really don't want to go into set theory. And set theory actually is narrower in this respect, because you can have categories in which objects don't form sets. See, there is something like sets don't encompass everything. For instance, you cannot have a set of all sets. That's a known thing, right? But you would like to have, category of sets. And if you have a category of sets, then you cannot say that objects in this category would be sets, right? But you cannot say, well, I have a set of sets, because such thing does not exist. So a way to bypass it is saying, well, you have a collection. What a collection is, it's sort of like a set, but more general, okay? And we are not going to go in this direction, right? So we have a bunch of objects, and we have a bunch of arrows. So the interesting things are about these things. Well, we call them like with letters F, G, and so on. You can have multiple arrows between two objects. You can have arrows that go from object back to the same object, and so on. So just think of this as like a very general graph, right? So a category is sort of like a graph. Except that usually when we talk about graphs, we think about finite number of nodes and edges. But in category theory, you can have finite number of objects, or you can have an infinite number of objects, or you can have uncountable number of objects, and you can have a number of objects that's not even a set. Okay? So that's much more general. So we have objects and morphisms. And every morphism goes between two objects. So for every arrow, you have to have the beginning of the arrow and the end of the arrow. Okay? Fine. Now, the most important thing about categories is composition. Okay, and this is at this point I could give you like a spiel that composition is like the most important thing in programming as well. But you probably know that already, right? Being able to decompose your problem into smaller problems and recompose it. So so whenever you are thinking about composition and decomposition, category theory is the theory of composition. So what's composition in category theory? Well, there are arrows that are composable, meaning a composable pair of arrows is two arrows that share one object. So the end of one arrow, let's say B, is the beginning of the next arrow. So that's very, very natural, right? So these arrows are composable because they touch end to end. And for every composable pair of arrows, so let's call it F and G, there must exist a composition. So the composition of F and G is usually called G after F. Okay? So notice that there could be many arrows between A and C, right? But only one of them is G after F, the composition of these two. Okay? Because often people get stuck with this idea that, okay, I have one arrow, why is this, you know, there could be many arrows, but this one is particular. It's a composition of these two. So a category is defined by the way you compose arrows. So instead of saying, like in set theory, we had sets here, and we could say a lot about a set by looking at its element. Here, we don't have the idea of an element of a set. So if you want to say anything about an object, we have to express it in terms of arrows. And we'll be going through these constructions using arrows to express all these things that we know about in set theory, we can express in terms of arrows. So this is the definition of the category. Plus, there has to be certain laws that have to be satisfied by composition. So there are the following laws. For every object, there is one special arrow from A to A, from the object back to itself, that's called an identity arrow. Identity at A. Okay? Every object in the category has to have this arrow. It can have more arrows from A to A. In fact, it can have a whole set of arrows. Okay? And here, the word set is used more often than not. Instead of collection, we say set of arrows. Because in most cases, arrows between two objects form a set. Okay, not a collection, but a set. It's possible to extend category theory so that they don't form a set. That's called enriched categories. But for us, this will be just a set. And the set of arrows between two objects is in a category C. So let's call this category C. A set of arrows between A and C is called a Hom set. Set of arrows between A and B. Okay, so all these arrows between A and B, they form a Hom set. Hom set. Why is it called Hom? Because I think it comes from homomorphisms. Originally, people were talking about homomorphisms between objects. So this is particular a Hom set from A to A, right? We would call it CAA. There's one element in this Hom set called identity at A. Okay? Why do we call it identity? Because there are these laws. Okay, so the identity law says that this is an identity with respect to composition, which means if you take this identity arrow at A and you compose with an arrow F from A to B, then you get back an arrow from A to B, the same arrow. Okay? So in this notation, you would say F after ID A equals F. Okay? And this is an interesting place when we say something is equal to something else. Okay? This is like opening a new can of worms. Because once you start saying that things are equal, then mathematicians start thinking, what does it mean, equal? Okay? In this case, it's simple because we said this is a Hom set. So these arrows actually form a set. So if two arrows are equal, it means that it's the same element of a set. Okay? And it will suffice for us at this level. They just form a set, and this is just equality of elements in a set. So this composition of two arrows produces the same arrow. And of course, the other way around, for the same, this is ID at B, let's say. So ID at B after F is the same as F, equals F. Okay? So these are called unit laws. Why do we insist on unit laws? Because maybe, can we have a category that does not have units? And sure, in mathematics you can do anything you want. So yeah, you can define something that doesn't have unit. However, it's really interesting to have structures that have these identities, because you can do one very important thing with identities. You can define things called isomorphisms. Okay, so morphisms are these arrows. Isomorphisms are pairs of arrows that go in the opposite direction. So you have F and G, two objects A and B. You say A is isomorphic to B if there is a pair of arrows like this whose combination is equal to ID. Okay? So you see F after G. So you go from B, you go G, and then you go F, and you get back into B, right? So F after G has to be ID at B. Because in general, F after G will give you some new morphism from this Hom set of B. Doesn't have to be identity. But if it is an identity and G after F is also an identity at A, so G after F, F and then G, is an identity at A. Okay? It means that these two things are like the same, really. Right? Because this, you can say G is like an inverse of F. So whatever F did, G undid, because you got identity at the end, right? So you take an object, you map it into some other objects, and then you map it back, and you get the same object back, sort of, right? This is a way of expressing this using only arrows. But it's like you have a round trip. It means these two objects have exactly the same properties. And you can show, in terms of arrows, they have exactly the same properties. Okay? So this is why we need identity laws. This is why we need identities and identity laws. Because we want to be able to define isomorphisms. And isomorphisms play a very important. So I said already about equality, that equality is a funny thing. Isomorphism is another funny thing. Okay? And it's like the whole homotopy type theory is just based on this fact. Is isomorphism the same as equality or not? When can it be the same and when it cannot? Okay? And the final law, and it's really extremely useful, because if we didn't have this law, our lives would be very complicated. It's called associativity. Associativity means that if you go from A to B, and then from B to C, and then from C to D, right? So you have three morphisms, F, G, H. That it really doesn't matter in which order you combine them. And by order, I mean not that you can switch them between, but you can do like, because composition is a binary operation, right? It takes two arrows and produces one arrow. So you can take these two arrows and produce an arrow here, which is G after F, right? Or you can take these two and produce H after G. And then you can take H after G after F, okay? H after G in parentheses after F, or you can do H after G after F, okay? And if these two things were different, then we would be in trouble, really, right? So this means that if you compose multiple arrows one after another, then you don't have to put parentheses, okay? And that really simplifies life. It doesn't mean that there aren't category theories, extended category theories in which this is not true. There is, it's possible to build these weak categories when this is not really true. But in most cases, this is really useful, okay? And in most examples, this will be true, okay? Time? There is still a little bit time? Yeah? Okay, okay. So this is all very abstract, right? I mean, this is like mathematicians even call this abstract nonsense. What do I want to erase? I'll erase this. And maybe I'll erase this as well, okay? Because I want to give you examples. So without examples, this is abstract nonsense, right? So, so the most important example for us is these objects are types, and these arrows are functions, okay? That's the model that we'll be working with as programmers, okay? Now, there is also a category of sets, and this is probably an easier thing to understand because you know what sets are. You don't know what types are, right? I mean, at least after my talk, you should not know what types are. But if you previously thought that types were sets, then it's okay. So sets also form a category, right? And so a category of sets has sets as objects, right? And morphisms are just functions, right? So so is this a category? How do we check if this is a category? Well, okay. So what's a composition in this category? We have to say what a composition is, right? So if you have two functions, okay. Where do I do? Oh, here, I see it. So this one is gone. So if you have function f and g, well, maybe we should call these types, I don't know, with capital letters, type A, type B, type C, right? What does it mean? So if you have an element, so f is a function, takes an x and produces something of type B. I don't know, I should probably use Haskell notation, right? So f is a function from, then I want lowercase letters, from A to B, right? And G is a function, okay, so double colon in Haskell, from B to C, right? So G after F. So in Haskell, we have the dot operator, that's composition. So G after F, when it's acting on some X from type A, is just defined as G acting on F of X, right? And you can define it in any other language. In Haskell, it's nice because you can define it parametrically for any type, and the notation for it is just like this, right? So in fact, you define this function for an arbitrary. So this is sort of a definition of dot, right? Dot is defined. The type of dot is it takes a function g, which goes from b to c, and it takes a function f that goes from a to b, and it produces a function that goes from a to c. Okay? So if you're not familiar with Haskell notation, this maybe looks a little bit complicated, but this is just this picture. That's it, right? F is this guy. No, this guy. F is this guy, right? So this is F, this is G, and this is G after F. The result of the dot operator. So this is a higher order function, right? Takes functions as arguments, takes this function and this function. This is infix notation that you can do in Haskell, right? That you can define an operator like this. So that's the nice thing about Haskell. It has very terse notation. So in the beginning it's hard, but once you get used to it, it's like you really appreciate the terseness of this. So this is function composition, right? And the next thing that we need in a category is we have this identity morphism, right? For every object. So for every type, there has to be a function from this type back to this type. And actually, we can define it once and for all. We call it ID. ID of x equals x. That's our identity. And you can easily convince yourself that if you compose identity after some function, then you'll get this function back, right? Because identity does nothing, right? So this is the do nothing function. Okay, now associativity of this is pretty much obvious, right? However you associate the three functions. Okay? So that shows that sets form a category with functions being just functions. I mean, I'm using Haskell notation, so I'm really talking about types, but it works for sets as well. I just don't have a good notation for sets, right? So this category of sets is called set originally. And I think that would be enough for today, right? Yeah. Okay. Thank you. Did I go over time? Yeah, not really.
So if you have any questions, raise your hand. And tomorrow we will continue, I think, not in this room, but in the one in front of this. But there will be signs, so don't worry. Does anybody have a question?
Right.
Well, that means that nobody understands it, but everybody understands it. So.
Well, what was the lie that I told you? Huh? Oh. Was there anything wrong that is not true?
Maybe the MDA people?
Yeah, but I said I wouldn't, right? Yeah.
So thank you very much for coming. It's really great to see that many people. And see you tomorrow and days after tomorrow.
See half of you tomorrow,
yes.
Right?